All right, we'll probably go ahead and get started. Thank you everyone for coming. It's my pleasure to introduce Ryan Bolt. Ryan is from Baylor University. He finished his PhD just this past August, so he's serving in a postdoc role with Baylor. He's with a part group out there, and he's actually somewhat new to the icing side of things, but the research he's been doing is very relevant to the icing side. So, Ryan, I'll let you take it over.
Thank you. Thanks for inviting me to talk. So my presentation is, it's about unusual types of roughness and how they affect airflow. And I'll start some background where the project really started was with roughness and additively manufactured cooling channels. So I'll talk some about that. Go over a background on PTV, so particle tracking velocimetry. It's the measurement system I use for most of this work. And then we'll kind of follow sort of a train of thought for research chronologically, studying cooling channels, working with sand grain predictions for different types of roughness that occurs there, and then moving on to looking at roughness predictions for wing icing accretion. And I'm going to be moving quickly over a lot of different topics. At the end, I'd be happy to go in depth on most of them. I'm going to try and cover a lot of ground and hope you have good questions. All right, so the motivation for the first area of research. Looking at AM cooling channel roughness because we want to be able to 3D print or powder bed fusion gas turbine components. The main benefits is complexity is generally free when making parts with additive manufacturing. We're finally getting good enough with superalloys like different variations of Inconel. This is starting to look more realistic. The main challenge is this process creates unique roughness. And many turbine components have very small cooling channels through them to keep the materials within their operating temperatures. And this roughness affects flow resistance through those channels and also heat transfer. So approach to figuring out what these effects are and whether or not they're important. Work with a scale model of a cooling channel. So it's a wind tunnel that's about 100 times scaled up version. And I'll take PTV measurements, analyze surface scans of the roughness, and also do some collaboration with people doing CFD models that are relevant to this kind of roughness. So the Penn State logo down there, several collaborators from that university. All right, so visual description of cooling channels. Could have just said pictures of cooling channels. So over here we have turbine blade. Kind of makes it easier to understand. During printing, the same turbine blade will be angled to one side. We have, this picture sort of shows a slicing program. You can see the different slices would go around the contours of the cooling channels here in the middle. And then this picture over here shows that if you have a cooling channel that is runs down the length of the turbine blade, it will be at an angle to the build surface. So as you change the angle that you build the turbine blade from, the properties of roughness change. So that's an important parameter. And just a quick note, I'm going to be talking about turbine blades a lot. Most of the research into this type of roughness is done assuming we're talking about turbine blades. They're actually kind of a bad candidate for additive manufacturing. Think about it, it's lots of layers of fused material on something that's being stretched to pull apart. So really, I think sort of the cowling and parts that surround a combustor are probably a more reasonable object to 3D print. But I'm referring to turbine blades a lot. So this wind tunnel, it's the Roughness internal flow tunnel. It is the scale model of a turbine blade cooling passage. Look right here, we have removable panels on the top and bottom surfaces. So we can put different representations of AM roughness on the top and bottom surface and measure what goes on inside. This is roughly, so depending on the panels we put on, this is a 50 to 100 times in large scale model. I think for all the surfaces I talk about, it's a 100 times scale. So the channel hydraulic diameter is 62 millimeters, and the actual cooling channel diameters are about 0.6 millimeters. All right, so I'm going to talk some about the measurement system I use. This is tomographic particle tracking. It's very similar to PIV, which is more common in research. We disperse reflective seed particles into airflow and track those seed particles so we can get some idea of how the air is moving. We use a system of cameras, so it's in my setup we have 4 cameras. So we triangulate the particles at one point in time, wait usually around 4 microseconds, and then take another set of pictures and locate the particles at a second point in time. So you have a delta t and 2 locations. That means we can get quite a few velocity vectors of air moving through the channel. Now, we usually take around 40. So like PIV, we average interrogation regions. So we usually look about 40 different seed particles, average together what they're doing. And so one more relevant piece of information is we are tracking something very small moving very quickly. For photography, we'd usually use a camera flash. That's not quite powerful enough for the sensors we're using. So we actually have a laser that flashes to eliminate the photos. Yeah. And a final point, each of these images, we have, this is just one camera at 2 points of time. Usually we can identify around 4 million particles in each one, and we'll match, I don't know, about 30% of those. So this matching process is very difficult. That's kind of the magic behind the measurement system. So here's a diagram that shows our setup more clearly. We have 4 cameras. We're dealing with large roughness that tends to obscure particles, so the system can triangulate with any 3 that see a particular particle. We can only track particles through the screen area, which is where a laser eliminates. And if you look over here, right, we have clear acrylic panels installed, so you can see what's going on. But these would be our rough test surfaces if we were testing. And I put this together just to kind of show the steps of data processing that we use. So we have 4 cameras. Each will take an A image and a B image. That gives us sort of one snapshot in time. So we get these instantaneous vector fields. They're very chaotic. We don't really have measurement density to get much that is meaningful here. So we repeat this process a bunch of times, usually until our computer runs out of memory. It's around 300 to 500 times, depending on how much equipment we have available. And we average it together to get something that looks a lot more reasonable. So you have a very dense vector cloud and filling a volume above the surface. We can't collect measurements fast enough for this to be a true time averaging. We're really sampling at points in time that are very slow compared to like the turbulence timescales. So it's really an ensemble average. But it's useful for the kind of things we're doing. Often we want to compare to CFD simulations or hot film probes. So we'll compress the data using spatial averaging, and that will give us a more traditional looking velocity profile. So we have distance from the surface down here, our velocity on this axis, and can track velocity through the measurement volume. And as you can see, this line is the mean roughness height. We are actually able to see below the peaks of the roughness elements, which was one of our goals, and we were happy that it worked out this well. On smaller roughness, we can actually see into the valleys, so below the actual mean roughness height too. That was a little less consistent. All right, so we talked about the measurement system. This is the thing we're trying to study with it. So additive manufactured roughness is a bit strange. If you just look at it, it looks purely random. But if you analyze, if you do autocorrelations, you find out it is periodic. You have repeating patterns, and it is directional. So if airflow hits it from different directions, there's different average angles it encounters, and it generally behaves differently. So the best description I can give for this without showing you just an STL file is that we have a regular pattern of ridges with random roughness kind of superimposed on top of that. And that makes sense if you think about how powder bed fusion works. So we're building up layers of fused metal powder. We get these regular ridges that are associated with each layer, and then the individual pieces of metal powder, as they melt and or sinter to the surface, that forms a more random texture. So other interesting qualities, the size of the roughness varies with print orientation. So if you have a channel, there's going to be some surface that faces upward during the printing process, another surface that faces downward on top. The downward-facing surfaces are built on unfused metal powder, so they're not as stable, and gravity tends to pull the metal into peaks. The upward-facing surfaces are a bit smoother, and so each channel gets to experience both of those, usually, on either side. And the final problem is that for the size of cooling channel we're interested in, the roughness is large. So the downward surface, the downskin, which is the upward-facing, the downskin, which is the downward-facing surface, tends to have larger roughness. So we have all these different qualities we're trying to make sense of. Sort of broke it into 3 separate areas to investigate. So we're going to look at print orientation, so what angle the surface is printed at, whether it's facing upward, facing downward, somewhere in between. Look at the roughness pattern angle, so the angle that those ridges, that air encounters those ridge-like patterns. And we're also going to look at surface feature correlation. I'll explain more of what that is in a minute. So first, print orientation. I've already talked about this some. Roughness is larger on downward-facing surfaces. We refer to those as the downskin, and smoother on upward-facing surfaces. This changes how the roughness affects the resistance to the channel. So if you have more resistance on one side, your velocity profile is going to be skewed towards one side. So if you're trying to quantify the effect of roughness, if you look at the side with the smaller roughness, it effectively sees a channel with a smaller hydraulic diameter. So when you want to investigate when we want to try and quantify these different types of roughness, the fact that the velocity profiles shift around is something important to consider. And also would likely be relevant to heat transfer. The second thing we looked at was roughness pattern angle. As I mentioned before, if you print your part at a different angle, these regular ridges are at a different orientation along the cooling channel surface. So we tested 4 different surfaces, printed straight up and down at 15, 30, and 45 degrees. And it turns out this acts sort of like rifling in a gun barrel. It induces swirl in the channel. This is one of the better PTV measurements. We had to demonstrate that. So we have red down at the bottom. That's flow sort of going span-wise in the negative z direction. And then we have slower flow returning over the top. So strong span-wise component, but it is deep, almost below a lot of it is below the peak roughness height. So we have a very strong span-wise flow right next to the roughness, and then a sort of slow correction over the top of the channel. This gets a lot more complicated if you have angled roughness on both sides. It's something I don't have too much time to go into here, but I think there's lots of interesting, it'd be interesting to investigate that more to see how it affects heat transfer, because you have some double swirling patterns and other interesting stuff. And the last aspect we investigated was surface feature correlation. So the reason this first caught our attention is in 3D printing, layer shift errors are extremely common. This benchy right here is a pretty extreme case, but if the layers of your print don't line up perfectly, you get this kind of shifted effect. Inside the channel, we suspect that would look like minimum correlation. So if your layer is shifted, you're going to have peaks on one side of the channel and then valleys on the other. And we guessed that this would cause the airflow to sort of follow the mean path, which would shift back and forth across the channel. To test this, we aligned 2 roughness panels that mirrored each other, put them on either side, and compared that to 2 roughness panels that mirrored each other and were slightly shifted. So we had a maximum correlated case where the peaks line up to peaks on the opposite side, and a minimum correlated case where the peaks on one side line up to valleys on the other. The maximum correlated, we expected that, because we were basically increasing and shrinking the diameter of the channel, that the airflow would speed up and slow down. And we saw both of these behaviors. Which we think would be interesting, again, to continue studying for heat transfer. What we did not expect is that although these behaviors were there, and we could see them very clearly, there was almost no change to the flow resistance. So from a design perspective, we've created the most extreme scenario we can to see if this is an important parameter, and there's no change to flow resistance. So the conclusion is this is probably something you can safely ignore. But if this flow behavior is useful to heat transfer, then maybe you could make use of it. All right, so I want to talk some about equivalent sand grain roughness. If you're a mechanical engineer, this chart is probably very familiar. Equivalent sand grain roughness is a very convenient way of measuring resistance in pipe flow. So you find some value of Ks that you say represents the roughness on a pipe. You can plug it into a Bernoulli equation in some form and predict your head loss, or how much pressure will change across that pipe. Its origins are kind of interesting. Someone took sand from a beach and started gluing it to pipes. Sand was all different sizes. He used a sieve, which meant he thought he had the sand that was from the size of the sieve, but you get a range of sand sizes that way. So it's kind of a flawed system conceptually, but through correlation, we've managed to make it a really powerful tool. Most engineering students are handed a Moody diagram at some point, and it lets you take the equivalent sand grain roughness, the flow parameters, usually Reynolds number, and then the diameter of the channel. So if you're able to take measurements and know the pressure drop across the pipe, it is very easy to assign a sand grain roughness correlation. We do that all the time. What's more difficult, and what we're trying to do, is look at the characteristics of the roughness, analyze those surfaces, and then predict Ks, so that we can estimate the pressure loss or other characteristics later on. Now, if you look at this channel, or I'm sorry, this diagram, you can see usually with a Moody chart, so most sand grain roughness correlation, you stop at about a 5% roughness height to the channel diameter, and we're looking at as large as 15%. So we're kind of in pushing the limits of how the system is meant to be used. So looking at roughness pattern angle, we want to see if we can, this is how we remember, we want to be able to look at different angles of printing these cooling channels and predict the changes that we'll have in flow resistance. So we'd like to be able to analyze the different roughness that occurs at each angle and predict KS, or sand grain. We analyze the surfaces using a bunch of different parameters. These include surface height statistics. So you look at the surface as a point cloud and look at variation across the mean height. And then some other parameters too, such as rugosity, like how crumpled the surface is, or the effective slope, or RMS angle. And those are basically relate to when the fluid travels across the surface, what kind of angles does it encounter? So we calculated all these parameters, and we looked at 3 existing sand grain roughness geometric predictions by Bonds, Sigal, Danberg, and Forooghi. And here are the results. So on this, you have the 3 predictions here. This blue line is the geometric predictions as you rotate the angle. And then we have our actual measured data. So we're able to measure the flow resistance through the wind tunnel, and those are our diamonds on the graph. So the Sigal-Danberg and the Bonds correlations did a pretty good job of capturing the changes that occurred at different print orientations. Forooghi wasn't too far off, but the trend lines don't match up very closely. So looks like these correlations aren't too bad, and you could refine them to create something that was extremely good at predicting flow resistance and adapting it to different print orientations. We're a long ways off, so I kind of included this diagram, sort of what the end goal of this kind of research and getting good at these kind of geometric predictions would be. If you had designed a part, you're able to put it into a slicing program. Based on the orientations and the different printing parameters, you could predict KS. CFD programs and heat transfer analysis generally is set up to work well with that. So that would be convenient for existing models. You could evaluate your design and kind of iterate. We're a long ways off from this, but this is kind of the end goal that I would share to kind of market this line of work. All right, so I'm going to talk about sand grain correlations and ice accretion. I was working on additively manufactured roughness for a couple of years, and my supervisor kindly reminded me that I am a member of the Baylor Icing group, so I should probably do something related to ice, and he set me working on this project. So geometric correlations seem to show some strengths even with unusual roughness. So we kind of decided to push those boundaries and look at ice accretion on wings. This is really just sort of to test the waters at their suitability. So the motivation, basically this would be very useful. Existing CFD models and ice prediction code generally works well with sand grain roughness, or is based upon it. So we would like to be able to look at scans, laser scans of actual ice accreted on wings, and relate those back to sand grain roughness. Now this is a lot harder than roughness inside a cooling channel for a number of reasons. So the whole concept of sand grain roughness is based around scaling on the hydraulic diameter of a channel. That kind of goes away. You have different length scales associated with flow around a wing. So we have chord length instead of the hydraulic diameter to deal with. The roughness is not consistent across the wing. So if you have this stagnation point and sort of march down across the wing, the nature of the roughness changes. And the final point is there's no straightforward method of evaluating predicted values. These are kind of used as a part of ice prediction code, And there's not a good straightforward method like there is with internal flow where we can just measure the pressure drop and say, okay, we have the correct Ks value. So here are our objectives. We're going to be able to develop and validate an approach to characterize these surfaces. We're looking at laser scans across an actual airfoil. And we want to be able to do the same kind of surface analysis that we've done in the past. So we want to see if we can get the surface characteristics accurately off of these surfaces, and then if we can generate Ks values from these surface characteristics that will change as you progress along the airfoil, and just kind of compare different models to each other. See, are they generally saying similar things? Do they scale well with different parameters, so like time, different chord lengths? If we change the angle of attack, and then if we change freestream conditions, are crazy things going to happen with these predicted parameters? Or are they generally stable or showing general, similar trends? So let's see what follows different scaling laws and see what kind of problems turn up. So I broke down some of the steps we went through. We have scans of ice taken at the NASA Glenn Icing Research Tunnel. We took these scans, we converted them to STL files and unwrapped them so that we have a flat surface that varies around a mean. That's important because that allows us to take surface statistics, which are how most geometric predictions are created. Once we have those surfaces, we want to use the different predictive models across the surfaces, and then we want to compare the results to the different models. 4 data sets were used, one with time scaling, one with different chord sizes, and we varied the flow conditions, so different angle of attack and different varying temperature. So first we need to convert from a laser point scan to STLs. This is pretty straightforward, but we needed to make sure this didn't change anything because we're going from a point cloud to a surface, and mathematically there's some differences there. So you can see we have our Icing scan here. We converted it, those surfaces that are defined as being, they're defined based on the flow direction, which allows us to unwrap it. The flow splits at the stagnation point, so we have sort of flow in the center moving outwards as we unwrap the surface, which looks something like this. Yeah, I suppose the important thing to keep in mind here, we can't unwrap based on the shape of the wing, but we have to look at the sort of the mean ice shape, which is something it's been developed in the icing world over time. I don't have expertise in that, but the result of using the mean ice shape rather than the wing is that you can look at roughness going above and below your medium height, which is important for the ways we characterize it. So first, we want to compare the statistics between the STL file and the laser scan with the statistics that work. So we can look at skewness and average roughness height on both types of files and compare them, just to make sure this conversion process isn't messing things up. And as you can see across these two parameters, there's generally pretty good agreement, so we continue. Next, we look at the different parameters used to create the geometric predictions. So we have the effective slope, and the effective slope modified for Sigal-Danberg parameter, plotted here. And then we also look at the RMS angle. So these, you can see changes across. So just a reminder, 0 is going to be the stagnation point, and then going away from that is around the wing. So we have linear changes in these parameters. Things don't look too chaotic, which is encouraging. And then here we show this surface scan is converted, and we have our sand grain roughness predictions. Just a reminder, these are I won't spend too much time on this slide. These are the 4 correlations we're looking at. We have the Sigal-Danberg parameter, one by Bonds, one's by Flack and Schults, which is currently used in Icing, and then one by Forooghi. And here are the results. So these are just the temporal scaling results here. So ice accretion over a period of time. You can see the Sigal-Danberg and the Bonds are pretty similar, and the Flack and Schults and the Forooghi are also fairly similar. Bonds and Sigal-Danberg show almost no roughness over the plateau region in the center. Then at the edge of the plateau, there's a large spike in roughness, and it trails off. The values are pretty similar as well. If you look at the Flack and Schults and Forooghi, it's almost an entirely different trend. There's not a big spike in roughness at the edge of the plateau. And if you get towards the edge, or farther back from the leading edge of the wing, you can see roughness gets a lot larger and then trails off. So we're just kind of comparing these to each other and not trying to say that either of these is correct. We don't have nearly enough information to do that. So finally, some general observations. Sigal-Danberg and Bonds correlations generally agreed in spatial variation. So as you march from the leading edge of the wing back to the trailing edge, they predict a similar change. Their peak roughness values were slightly different, more similar than with the Sigal-Danberg and Flack and Schults, but there were some differences there. The Flack and Schults and Forooghi correlations generally agreed in spatial variation, agreed with each other. In the feathering region, so as you move away from the plateau region, which is the front of the wing, roughness sort of increases linearly and then trails off. And then if you look at the Bonds and the Flack and Schults correlations, they both exhibit similar maximum sand grain roughness values, as do Sigal-Danberg and Forooghi. So again, we can't really draw conclusions that any of these are working better than the other. But if using these in Icing codes is valuable enough, they seem to be consistent enough that working with geometric predictions could have some value and would be worth investigating further. So some acknowledgements. My advisor, then supervisor and friend, Dr. Stephen McLean, the Baylor Icing Group, co-authors and collaborators, Drs. Kunz, Hansen, and Yang. They're at Penn State, and they helped a lot with CFD models that we kind of went back and forth with, looking at flow within the wind tunnel. The AM roughness studies were made possible by a grant from the Department of Energy. And then the laser scans of ice accretion were all from a series of studies conducted at NASA Glenn. So now I'm happy to take questions. Yeah.
So the roughness of the wing, that's without icing. You're just looking at the wing before icing occurs. Is that correct?
We're looking at just icing.
So okay, so you so you're taking measurements of wing with icing on it already?
So with all the laser scans we used, that was when ice had already built up on it.
Can you repeat that?
With the laser scans we used, ice had already built up on the wing.
Oh, okay, okay.
You see along here, this red line is the actual wing surface. You can see the height of the ice on it. we're not really seeing much of the wing itself at all.
So if you would use prediction models, would the roughness change over time?
Yes.
So it would kind of start with smooth and then change.
Right. So it does develop over time. We're looking at when it's already developed. And part of the prediction models is as ice develops, it changes the roughness, which changes how ice develops in the future. So getting that right is important because it kind of is a feedback.
Yeah.
We're not really looking at the early stages of that. Yes.
What droplet size or range of droplet sizes were used in this experiment?
I could find out, but I don't know.
Okay.
What was the icing amount that you already have on the mix, like icing rate or icing amount? You start with some icing, right? So what was the amount? Because depending on how much initial icing you have, your calculation will change, right?
Yes, so we're not trying to predict icing over time. So if we're just, so we did look at icing over a period of time. That was more to see that the models weren't changing drastically as ice changed over time. We didn't, we weren't trying to predict anything. And so I don't know the starting amount.
Okay.
I'm sorry. Yes.
I have a question about the sand grain roughness parameter. So if I understood correctly, you have this scan of the roughness that's observed, and then you're taking the properties of the roughness to predict the K value. And so I was wondering that K value that you predict for I guess one section of the wing, if you were then to put that in a pipe, could you then use the K value the same way that you would in the pipe flow and get the same pressure drop type of thing?
So it's an interesting question. You probably could. The problem is we're almost using sand grain roughness to mean something else in this situation. But I mentioned the analogy has changed. External flow and internal flow are very difficult to relate to each other. So I've actually done some thought about how we would, ways of verifying that, and I don't have any good answers. Part of the problem is when K changes, you have air traveling over and experiencing a bunch of different roughness values. It's hard to know if that relates back well to pipe flow. And I think in a pipe there's a set limit to where your shear is being experienced, and then over wing, you kind of have to artificially say there's a cap to the boundary layer. So then you have to make arguments about where that is. So it's possible. It'd just be a lot of work to see if that. It's worth. I think that's a rabbit hole worth following. I just don't know the answer.
Interesting.
Yes.
Can you go back to the misalignment of your surface 3D printing part? Yeah, this picture. So on the lower left, does that represent the actual pipe and the top of the pipe and the bottom of the pipe, or just between two very thin layers? I'm kind of being misguided by the scale of those peaks and valleys. So could you explain a little bit more?
Yeah. I'm actually going to go back to this image. This shows two actual surfaces.
Right.
Down here, this is our largest downskin surface. This is what we used in testing. So for maximum correlation, so for this case, we mirrored those surfaces.
I see, on top.
So everywhere there was a peak on the bottom surface, there's a matching peak on the. For the minimum correlated, we used a autocorrelation program on the surface. So we looked at repeating similarity. And we shifted the top surface a certain amount to the point where it was the most dissimilar. And we put that test surface on top. Does that answer your question, or are you asking something?
Yeah, I think that sort of answers. So basically, the gap between these two layers is much bigger than the feature of the roughness itself. Or
Yes.
okay,
So the features extend about 15%.
yeah, 10 to 15%. Yeah.
Okay, so yeah, you did cover a lot of stuff. So I'm going back to the particle tracking velocimetry. Okay, yeah. So I was curious. So you mentioned that you'll kind of the voxels. You'll take like roughly 40 particles and sort of they will all have a single velocity vector associated with that group. And it kind of reminded me of the super droplet method. But I was curious if like there's a way that you use to like you know that 40, those will all have the similar properties, or is it kind of just limited based on how much data you have, or is there? I guess the question is there a justification for how big your voxel area can be and represent those droplets?
So, again, great question. You're digging into. I could put a 3-hour-long presentation on PIV. I'd love it. I don't know if anyone else would. So I gave 40 as a number for an individual. It's like one set of pictures, so one instantaneous field, and that was our cutoff. So to create a vector, we had to have at least 40, otherwise we eliminated it. As to why 40 is significant, there's not a, just to find 40 as a number is going to change on based on a whole bunch of other parameters. The way we verified things is we looked at individual height, sort of slices of height across our measurement volume, because we knew there'd be a consistent velocity, a consistent mean velocity at each height. So we have a velocity profile across the channel. So we looked at basically a statistical spread of all our vectors in each component and made sure they were varied around the mean height. And then we could check all our vectors within at that height and made sure they weren't drastically different from the average across the mean. So when we had a top and a bottom rough surface, our laser light was scattering all over the place. So we were getting, where there was better light, we'd get more measurements, and we get fewer measurements where there was worse. So we had to do lots of processing to make sure we weren't biasing measurements to a particular area. So we looked at a lot of things like that really closely.
Okay.
Fairly confident.
Yeah.
Can I follow up and comment on that? Does that mean your flow structure and feature probably have certain either freedom of degree or certain features being able to capture by 40 of these tracers to kind of reflect the overall statistics of them? Because if you have a fewer, you might miss certain scales or you miss certain structure. I'm curious, is that kind of the idea? Because when Elise talk about super droplet, which means for a size distribution of our droplet, we need to have a certain representation of those range, and only certain amount of that would give you the right description of the size distribution. And here, is that the same kind of idea that have to have that many to give you the feature of the flow?
Yes. So yes, I think that's the case. So 40 is for an individual set, for one instantaneous set of measurements. And we're taking between 300 to 500 instantaneous and averaging those together. So an individual voxel, we're getting quite a few more particles that go into each vector.
Gotcha.
And then we're evaluating the vectors based on what all the particles are in, to make sure they're representative of the several thousand particles in a particular space. I don't know if I'm doing a good job of answering your question. I'm not
I
too
sort of
familiar with.
get it, yeah, but not exactly, but thank you. That's actually helpful.
I guess, yeah, for still wanting to understand the voxel area. So in the system, is it assumed like a steady state, like it's not going to change over time what the vectors are doing, what the velocity vectors are doing?
Yes.
Okay.
Our measurement system operates at 15 hertz, which sounds fast, looks fast, but compared to the looking at turbine flow, so lots of spinning eddies, the fluctuations we'd expect to see from those are much faster than our rate of capturing data. You can look at eddies eddies get faster as they get smaller. So we can look at the eddy size that we would pick up with with the size of our voxels. And we know that we're a long way from seeing those. So when we average our data to these ensemble average vector clouds, we're really getting just the mid flow.
Got it.
And our wind tunnel should be fully turbulent. There's kind of a good range where it works well. And if we get too slow in the wind tunnel, we'll have fluctuations. There's some transition, and that will cause problems. I think similar to what we were talking about.
So the voxel area corresponds to like a certain spatial location, and you can build up the statistics in that area over time.
Yes. And so the voxels are 1 millimeter cubed, and they overlap. So you can do some fancy stuff using voxels to smooth other voxels. I think that's a bit questionable unless you have lots of good reason to defend doing that. But our voxels do share particles because there's overlap. Yes.
Yeah, I was wondering, is there for the ice accretion, like, is there also like melting happening, say at the contact of surface with the, say the plane or the, in that case, do these codes consider the heat transfer between the solid surface and the ice being accreted on it? And also its impacts on like the roughness calculations.
So I know that is something people who study developing icing look at. I don't have any expertise on that. So I know that that kind of behavior causes the roughness that I'm trying to quantify. But I don't know too much about how it works.
When you do the laser imaging of the wing surface, going back toward the end of your talk, how long does it take to do the actual laser imaging of that?
So we collected a bunch of data sets that were taken between 2014 and 2020. I didn't know what accretion was when they were doing that, unfortunately. And the articles that they published don't. I didn't see anything about the time.
So you basically use their data and then.
Yes.
there any questions online? Any other questions? All right.
Fascinating.
Thank you, Ryan.
Thanks.